All right, so here we go again. We're getting close to wrapping up this unit on energy and heat and in the Earth system. So what we're going to look at today is we're going to wrap up a little bit of what we talked about with gas laws, and then we'll go into a little bit more depth regarding what's going on with the motion of those particles, how those particles can transition from one state to another, and we'll talk about what that means as well. But before we go, again, I want to make sure that we always keep you guys engaged. Somewhere inside this lecture, I'm going to tell you a joke. So make sure that you're paying attention to that, and when you get the joke, then you'll know that we're about halfway done. All right, so here we go. What we talked about in the past was this thing called the kinetic energy of particles. We talked about how no matter what happened, particles are in motion. And we said that the temperature, we've said this has to be at least the third time, maybe the fourth time, that we've said temperature is the average kinetic energy of the particles of a sample. So what we end up looking at is if we had a sample of a gas. So if we drew a picture, here's our picture of a gas. There's actually two gases that we put inside this container. And if we're saying that they are at the same temperature, these are the same sample at the same temperature, the same pressure, they're moving around, but something has to be a little bit different. If these are the same temperature and the same pressure, you'll notice some of the dots are those really big blue dots. You can't really tell the color because of the way my screen is, but the bigger dots were blue, and there's these itty-bitty tiny little red dots. So here's the deal. If these particles are both at the same temperature, how is it possible that they have the same kinetic energy? So remember, kinetic energy is a combination of not just their speed, right? It's not just how fast these things are moving around. The other thing involved in this is the size of the particles. So if these were the same two particles, well, two different particles, sorry, a large particle and a small particle. If these particles are at the same temperature, that means they have the same kinetic energy, which means that these blue dots are going to be moving much slower than the tiny red dots. The tiny red dots are going to be moving much, much faster in order to have the same kinetic energy. That is what we're talking about with this idea of temperature, that the particles that are larger will be moving slower, but when they make a collision, they will have the same amount of energy as a small particle bumping into the walls of the container. So this is where we start to understand differences between getting hit by a car and hit by a skateboard. I wouldn't mind if a person on a skateboard bumps into me if they're going about 10 miles an hour, right? 10 miles an hour is pretty good speed. That's about how fast people in our PE classes run the mile. Like, you should be able to run a mile in about 10 minutes if you're actually running, right? So 10 miles, you're jogging. So a sidewalk collision of somebody jogging versus a sidewalk collision of a car pulling out of the driveway at 10 miles an hour. You would feel both of them. The car would give you a lot more energy transferred into you because it has more mass. These larger particles have much more mass. They will pass that energy into the walls of the container, and it will allow the pressure to be greater. For these small particles to be able to have the same amount of energy, they would have to be moving much, much, much more rapidly. All right? So throughout this whole thing, we just keep talking about this idea of the kinetic molecular theory. The thing about kinetic molecular theory is this. There are 5 premises that we have to pay attention to. With these 5 premises, that's how we know that we have a sample that is undergoing something about kinetic molecular theory. All matter, everything in the universe falls under these 5 categories. Right now we're looking at it specifically about the gases that we've been talking about. So with the gases, the first thing that we're saying, all particles, gases, liquids, solids, plasmas, they're all in constant motion. And that constant motion continues no matter what state of matter they happen to be in. They're moving all the time. The more energy they have, the greater that kinetic energy, the greater that motion will become. The second premise of the kinetic molecular theory is that the particles are so far apart that the gas is mostly composed of empty space. Now, this is one that's a little bit more difficult to understand. We are literally saying that a sample of a balloon, when I blow into the balloon and it fills the balloon, what we're saying is the balloon is still mostly filled up with empty space. There's so few particles that if we were to look inside, those particles are moving around, and it's like there's no particles there. We're saying that the volume of the particles is so tiny that we can ignore the sample of the particles, and we're just looking at the volume of the balloon. This is still, it's one of the more confusing things about science and about the kinetic molecular theory. You're telling me that I'm putting particles into a balloon, but it's like they're not there. They aren't. The volume of the gas is the size of the container. We don't care about those itty bitty little particles. They don't take up very much space, all right? The third premise is that there are no noticeable forces on the gas particles. We are saying that if it's a gas, they're flying around, they collide with each other, but there is no attraction, there is no repulsion. Literally, these particles are moving around, and it's as if they were not even there together. They ignore each other. They only do what they are doing. There's no attraction, there's no repulsion, they just keep flying around. And as that continues to happen, something else takes place. As we continue this, those collisions, since they're not being attracted and they're not being repelled from each other, there's no repulsion, when they bump into each other or when they bump into the walls of the container, it is what we call an elastic collision. This is a physics term that you'll learn more about later in your life, but an elastic collision essentially says there's no loss of energy. It bumps into the wall and it rebounds in the other direction with the same amount of energy that it had when it first collided with the wall. If it bumps into another particle, they move off with the same amount of energy as they had when they collided. There is no loss of energy in those particles. And then the fifth and final premise of this is that the temperature is directly proportional to the average kinetic energy of the particles. Again, we've been talking about what temperature is, so now we're saying that because of that kinetic energy, that's going to determine what's going on. This is based on the absolute temperature scale, and that absolute temperature scale says that at 0 Kelvin, there is zero motion. At 100 Kelvin, there's some motion, and at 200 Kelvin, there's twice the amount of motion that there was at 100 Kelvin. And as we continue to increase every 100 degrees Kelvin, that is another set of doubling from 100. So we go 100 to 200, it's doubled. We go from 200 to 300, not doubled. That's not the right math. It's proportional. So if we went up from 0 to 100, then from 100 to 200, from 200 to 300, each of those 100 Kelvin intervals has the same amount of change on those particles. So from 100 to 200, it doubles the amount of kinetic energy. If I go from 200 to 300, that's not doubling, that's 3 times more energy than 100 Kelvin had. Does that make sense? 100 times 3 would be 300. So it's 3 times more energy. This is a kinetic molecular theory. This is what we talk about, and we deal with ideal gases all the time. So these kinetic molecular theories describe what we call an ideal gas. So an ideal gas is a little bit different as well. We say that we have ideal gases. This term, I don't know if you can see it on my screen. Let me check. Okay, yeah. Ideal gases are what we deal with on our everyday basis in our world. The problem is real gases are what really exist out there in the world. Okay? So in an ideal gas, they do not do what we would normally expect to happen. A real gas is a couple of those premises are wrong, right? Because we know that there are particles. And particles have mass. And what was the other thing of describing the definition of matter? They have mass and they take up space. So real gases have volume. A real gas, those little particles, they're going to have volume. They're also going to have an attraction for each other. So that attraction means when they're flying around, when they bump into each other, they might actually stick and become a larger molecule or start to even become liquefied. So real gases have volume, they have an attraction, and then even sometimes if they're different gases, they may even repel each other. They might push each other away. So those are the things that make a real gas different from an ideal gas. The other thing is, how do we make ideal gases become real gases? They would have to be at low temperature. Think about what we've been saying with our gas laws. If we cool the temperature down, the particles begin to slow down. And when they slow down, those collisions won't be as energetic. And now when they hit together, they might actually stick. So ideal gases begin to behave like a real gas at a low temperature. And then what else could we do? What if we increase the pressure and we push these particles really, really close to each other? Well, if we allowed them to get close, again, they're going to collide more often, and now they can't really get away as much, and there might be more of an attraction. So we say that real gases begin to occur at low temperatures and high pressures. The problem with that is that's not what we experience in our everyday lives. In everyday lives, if I can get this to show up right, oh, what just happened? Where's my menu? There it is. A real gas almost, dumb computers. We always use the ideal gases because we live in a condition where our temperature isn't low enough for those gases to stick together. Our pressure isn't high enough to be able to stick those particles together. Under normal conditions, all the gases that we deal with are going to be ideal gases. That being said, we still need to recognize that there are these things called real gases. And so that's what we're looking at there. So what all of this leads to is now as we begin to look at all this stuff about gases is what will happen if we start to change the amount of energy that we've got. So we've got these particles at high energy. If we start to slow them down, they start to become liquids, and then we can turn them into solids. So now we're going to look at a little bit of a transition. We're going to look at what happens when we either put energy into a system or we take energy out. The adding and removal of energy is what causes that change of state. So remember, what is a change of state? It's when a substance changes its physical properties to be a little bit different. A gas has no attraction for each other. Those particles are flying around. But when they become liquids, they will stick together. Then when they become liquids and they're moving around, they're really, really close to each other, but they still don't like each other. All right? So, like I said, before we transition, I did want to tell you one joke. Here's your joke. Well, actually, I'll tell you two. So, I used to hate facial hair, then it grew on me. That's your first joke. So now, these changes of state. You've already recognized these from previous life experiences. They are melting and freezing, vaporization and condensation, that's the terms for them, and sublimation and deposition you may not have heard before. These are like the high school level chemistry terms of something else that can take place. But the idea that we've talked about in class a couple times, melting and freezing happen at the same temperature. Melting is a solid becoming a liquid, and liquid becoming solid is called freezing. So these are the transition terms between solids and liquids. Vaporization and condensation are between liquid and gas. So when a liquid becomes a gas, we call that vaporization. Now there's a small little step that we have to keep in mind here about what's called vaporization. Evaporation is what you know of. You spill water on your table, you kind of wipe up most of it, and then it goes away. Evaporation takes place at any and all temperatures. It's when the liquid particles gain enough energy to be able to escape from the liquid and they become vapor. They become a gas. That can happen at any temperature. But boiling is a very specific type of vaporization that we talked about the other day. It's when the particles have enough energy to escape and the pressure of those liquid particles is equal to the atmospheric pressure. That happens at very specific temperatures, and if the pressure of the atmosphere is 1 atmosphere of pressure, or 760 torr, or 760 millimeters of mercury, or 14.7 psi, if any of those that we've talked about, if that's the atmospheric pressure, the temperature of water to become a gas, it has to be 100 degrees Celsius. At a lower pressure, it requires a lower temperature. We talked about that the other day with the bell jar, and you should remember that. Condensation is just the reverse process. So when your cold beverage gets wet on the outside, that is condensation. That is nothing coming from the inside of your cup. That is coming from the air around you. There's water vapor in the air. When it bumps against your cold beverage and it gets water drops on the outside, that is condensation. All right? The last one is sublimation and deposition. Now again, this is a little bit deeper, a little bit more complicated to understand. It is when it skips the liquid phase. So what we're saying is going to happen here is this is a solid going straight to a gas, or it's a gas, this one, deposition, is a gas going to a solid, if I can learn how to write. So sublimation is what dry ice does. Sometimes in your freezer, you will notice that your ice cubes shrink. That's because the solid skips over becoming a liquid and goes straight to the gaseous form. Deposition would be the opposite side. In the wintertime when there's frost on the ground, it's because there was no dew, it was water vapor in the air moving around, and it bumps into a cold surface, and it immediately freezes. That is called deposition, kind of like making a deposit. It's being deposited as a solid. There's no liquid involved in that at all. So through these processes, what's going on is how we deal with these energy changes. To go from a solid to a liquid, I have to put energy in to make the particles move more. Remember we said the kinetic molecular theory had solids just kind of vibrate. And then liquids move past each other. And then gases have no attraction. There's nothing going on. They just move around randomly. All right? To go from solid to liquid, we have to put enough energy to break those particles so close together. They're still really close, but they have more freedom to move around. To go from a liquid to a gas, we have to add even more energy to break them apart. To bring them back, we're taking energy out of those systems. So we'll talk about this in the next couple of days, probably in the next video. We'll talk about what it's called when you put energy in and we take energy out. So what we're going to do is tomorrow, which is going to be Tuesday in class, we're going to do a lab. This lab is called the Icy Hot Lab. I'm going to show you what the setup's going to look like, and then I'm going to show you how you're actually going to go about doing this. Then, as you make your careful observations and you make data in class on Tuesday, we'll talk on Wednesday about what we should have learned through that. So I'm going to set up the system and then let you see what that's going to look like. So this is sticky. This is why I need a camera person, one of these days.